So good morning students. So in this class we are going to discuss about inverse Z transform. So in that inverse Z transform corresponding to finding x of n. So given x of z and its ROC. So the Z transform and the inverse Z transform are one to one mapping provide that the ROC is given x of n lies between x of z. So there are four commonly used techniques to evaluate the inverse Z transform there. So inspection, partial fraction, expansion, power x series expansion and Cauchy integration theorem. And the inspection method is there is long division method. So when we are familiar with a certain transform paths, we do the inverse Z transform by inspection, that is long division method. So determine the inverse Z transform of x of s, which is expressed as x of z which is equal to z divided by 2ez minus 1, where modulus of z greater than 0.5. So first we write as x of z which is equal to 0.5 divided by 1 minus 0.5 into z power minus 1. So making the following transform in the table a power n into u of n lies between 1 divided by 1 minus a into z power minus 1, where modulus of z greater than modulus of a, and putting a which is equal to 0.5, we have 0.5 divided by 1 minus 0.5 z power minus 1 lies between 0.5 into 0.5 power n into whole power n, which is equal to x of n which is equal to 0.5 into n minus n plus 1 into u of n. And the next method is partial fraction expansion. So it is useful when x of n is a rational function in z power minus 1, and this is x of z which is equal to summation k which is equal to 0 to m and bk into z power minus k divided by summation k which is equal to 0 to n ak into z power minus k. So for pole and 0 determination, it is advantageous to multiply z power m plus n to both numerator and denominator, and x of z which is equal to z power n into summation k which is equal to 0 to n bk into z power minus m minus k divided by 2 power m into summation k which is equal to 0 to n into ak into z power n minus k. And when m greater than n and there are m minus 1 poles at z which is equal to 0, when m less than n there are m minus m 0 at z which is equal to 0. So to obtain the partial fraction expansion from, so the first step to determine the n non-zero poles and c1 c2 up to cn. So there are four cases to be considered. Case 1, so m less than n in all poles and first order, and for first order poles all ck are distinct x of z is, so x of z which is equal to summation k which is equal to 1 to n ak into 1 minus ck into z power minus 1. For each first order term of ak divided by 1 minus ck into z power minus 1, it is in inverse z terms can be easily obtained by inspection and multiplying both sides by 1 minus ck into z power minus 1 and evaluating for z which is equal to zk. So ak which is equal to 1 minus ck into z power minus 1 into x of z divided by z power minus 2, and for computing a1 and n which is equal to 2 greater than m is x of z which is equal to a1 divided by 1 minus c1 into z power minus 1 plus a2 divided by 1 minus c2 into z power minus 1 is equal to 1 minus c1 into z power minus 1 into x of z which is equal to a1 plus a2 into 1 minus c1 into z power minus 1 divided by 1 minus c2 into z power minus 1, and substituting z which is equal to c1 we get a1, and these three steps are first you have to find the poles and find ak and perform inverse z transform for the fractions by inspection, and find the pole and 0 location.